be a part of FDP, and it's very ambitious to be a part of this online FDP where we are talking about the interconnection between the lab and the industry. So the topic for today's talk is a roundup of secondary batteries with focus on electrode materials. So this is the overview of my talk. I'll be talking about a bit of carbon footprint, why renewables are required, what are the other options available to us, then starting with the batteries, and then speaking more on the anode materials. So as Dr. Pragya informed that yesterday there were sessions from MNRE about renewables and our journey from, I think, 1970 was the year till now. So what I do is usually whenever I talk about batteries or fuel cells, I also incorporate a bit of the background why it is important to be sensitive towards these requirements of the hour. So you will see maybe it will be a bit of overlap between the sessions that happened yesterday, but it's an academician's point of view and academician's interpretation that is there that I'll be presenting first. So this is going to be the flow of the talk, and we'll start with the first questions, that why carbon footprint and why renewables. So the answer to this was, you can say there was a study in 2009. It's a Nature publication which talked about a safe operating space for humanity. So it really goes to the core of the existence of humanity. And in this paper, the authors chalked out that there are 9 planetary boundaries. What are these 9 planetary boundaries? You can look at the climate change over here at the top. Then chemical pollution, it's not yet quantified. Atmospheric aerosol loading, not yet quantified. Then biodiversity loss, changes in land use, global freshwater use, phosphorus cycle, nitrogen cycle, catastrophic ozone depletion, ocean acidification. So these are the limits that you see on this figure. And out of these, in 2009, we were already in the red zone for 3 of these 9 boundaries. What defines these 9 boundaries is Earth has a special ecosystem which can sustain life. And if we are disturbing it, soon there will be conditions where the living conditions or habitating conditions will not be conducive anymore. And this was an alarming paper. The author and the team further took stock of situation in 2015. And here you can see that we have gone from bad to worse. We have crossed the zone of the genetic diversity. The phosphorus and nitrogen cycles are also shown in red, which means that's beyond zone of uncertainty and we are at high risk. And there are a couple of question marks over here in biosphere integrity, functional diversity, novel entities, and atmospheric aerosol loading, where we yet do not know how to quantify them. So it is pretty possible that we are either in the alarming situation or we have already crossed the zones, but presently we do not have the tools and techniques to quantify these boundaries. So this becomes very crucial, that why we have to respect these planetary boundaries. We have already started seeing the changes. For example, I was speaking to a colleague just 2-3 days back, and it was incessantly raining in Pune. And the person was saying that never ever it has rained so heavily in September in Pune. Same situation I heard from another acquaintance who was in Uttar Pradesh just 4 or 5 days back. So we are seeing these changes which are happening. These we call them under the umbrella of climate changes. Then we also have biosphere integrity and biogeochemical flows. So this is where the nitrogen and the phosphorus cycles were being talked about, and the land system changes. So I'll touch upon why we need to be sensitive regarding whatever activities are being done by the human races. Sorry, just like I'll start with the climate change. We know that the temperatures all over the earth are changing, and we have to limit the rate at which the earth's surface temperature is rising. If this is not stopped, the few very prominent changes that are known to us, that wind patterns will change, climatic conditions will change, we will observe melting of glaciers. But what we do not pay attention to is there would be certain species which are living in those regions of earth which are not yet habitable, and there if these climatic changes are happening, then they may lead to movement of these species into places where humans stay. And when such species, which yet we do not know of, the biodiversity that we keep hearing about also talks about many species which will transform because of these climatic changes. And when they interfere with the human ecological system, what kind of diseases they will bring in, what kind of pandemics we will be having, we don't know. COVID 2019 has been just an eye opener for all of us. We know, of course, we don't know yet that what was the cause of the outbreak, but the predictions were, or the main expectations were, that the bats were the carriers of these viruses. So just imagine, we are right now in the unknown. We don't even know what kind of species are there in those areas of Earth which are not habitable, and we don't know what kind of species are interacting. So when these climatic changes take place, when ecological changes take place, they may be coming out of those zones, spreading all over, and how human race is going to interact with them, we don't know. So new diseases whose vaccines we don't know. There are many challenges. It is just a big X for us at present. So therefore, it is very important for all of us to respect these boundaries. And with this, I now start with the platform of why do we need energy. So energy, first of all, is also taken as an indicator of the growth of any nation. And as advancement in science and technology is happening day after day, we are becoming more techno savvy, we are becoming more gadget dependent. A lot of automation is also happening. So to run all these, we need energy, we need power. With this, I would like to draw your attention to the world energy consumption data in 2012. If you look at 2012, about 52% of the energy was being consumed by the industries, and the next highest was by the transportation, which was about 27%. Now, let's see how things have changed now. So this is the renewable, sorry, this is the Renewable Energy Roadmap till 2050. Of course, we have to keep in mind the renewable energy, because we want to make ourselves less and less fossil fuel resources independent. So here again, we talk about the power share over here, which is 58%. And transport has just shrunk to 13%, because now as we move ahead in time, of course, we are not saying that the transportation consumption is going to lower down. No, with population, even this is going to go up. But as population increases, energy demand is increasing. And in that perspective, the share which is going to go to transport is now almost half. We just saw that it was 27 or 26%. Now it will become half of what it was in 2012. And mostly 58% will be governed by other activities. So therefore, we need to be little sensitive about what kind of energy means we are using, and what kind of energy production we are adopting to fulfill the demands. So hence comes the question of the carbon footprint. So we have already entered the Anthropogenic Era. What is this era? it is when human interventions or human activities disturb the ecological system of the earth. So we talk about the carbon footprint. There are many activities which lead to the emission. I'm not going to list them one by one, but what I would like to draw your attention to is that there are different aspects of looking at the carbon footprint. So here we see you can see the scope one, which is direct. So if let's say that you have a fuel combustion, which is happening and you're consuming it, or you are um, using a company owned vehicle, then whatever emission is happening, that is happening directly into the environment. And that is scope one, which is the direct emission of the emissions in the environment. But then there are indirect uh, venues also. For example, when we are purchasing the electricity for our household use, the production is happening somewhere else. We are the end consumers, but that production is happening somewhere else. And hence, we cannot ignore the emission which has happened at that stage. Similarly, when we are using public transports, the waste disposal management, or any product, any other product that we're using, there also some amount of emission has taken place. So we have to be little sensitive about these kind of emissions. Now, let's say that everybody these days uses laptops and mobiles, basically portable devices, where there is some kind of power generating system, the batteries, which is the topic for today. So now let's say that I'm very vigilant. I take care of not recharging my gadgets. So whenever the charge is close to 100%, I ensure that I switch off the supply. And whenever the battery is about to die down to 33%, I ensure that I have recharged it. But what I'm doing is that I'm techno savvy, and every year or every 6 months, I want a new gadget, I want a new mobile. So is it that being sensitive enough? Does that solve the purpose? The answer is no. Because for every product that has been manufactured, there is a lot of manufacturing emission which is going on. And if you look at this balance, the carbon scales, the usage is just a small proportion of whatever emissions are happening at the manufacturing side. So this sensitivity should be in all of us. Further, in Olympics 2020 in Tokyo, if you remember, uh, they had almost created a net zero kind of games where even the metals which were forged in medals, those came from the devices which were recycled. Okay, so therefore, the recycling, reuse, and refurbishing are actually activities which should be taken up to save the environment. One welcoming thing, if you look at this graph, is that the global carbon emission has fallen in the year 2020. Okay, so you can see that almost every country, and including the world, logged a deficit in the carbon emission. But we should also remember that this was the era when this was the year in which most of the countries were under lockdown. And this is a direct indicator that how human activities are actually interfering with the ecological systems of the earth. And remember the first slide, the planetary boundaries. So it means that the nature will self-heal itself, but our activities have to be kept under check. Going further on this, if we look at the energy consumption from 2000 to 2020, then what we see is that the fossil fuels over here again are logging a deficit in their percentage increase, and the nuclear, hydro, and other renewables are growing. So, which is a positive indicator that countries and the governments are becoming more sensitive towards what kind of means one is using to produce the energy. So here again, we see the journey from 2000 to 2050. Of course, these are the predictions over here, that how the sectors are going to grow. The hydroelectricity, if you see, is supposed to maintain its increase. Please remember, on the y-axis, we have exajoules. So exa stands for 10 to the power 18 joules. So it's even though the change may be minor, we are talking about huge differences. Good thing is that if we talk, sorry, if we talk about the coal, which is shown over here, the natural gas and the oil, they do not show any rise. And the welcoming step is the gray bars, if you can see. So you can see that in exajoules units, the ratio or the proportion of renewables is increasing. Now, of course, when we talk about solar energy or the wind energy, the main challenges about these two are about the fluctuations and the intermittent availability of these sources. So therefore, they cannot be fully dependent upon. So this is something that one must keep in mind. Please excuse me for a minute. Sorry about this. So then what is the hope that we have? So there is some hope certainly that if you look at the figures for renewable capacity growth in 2021, the entire world has shown a 9.1% increase. And of this, solar and wind are the main stakeholders over here, and which are equal 27% and 28%. And now what we need to do is we want to increase the share of these others over here. Of course, presently the dominant is hydropower. In Asia, if we talk about Asia, not the world, then the growth that has been seen is about 11.9%. And in the renewable power capacity, if you look at this chart, then what we see is again the hydropower has maintained the growth from 2016 to 2021. Solar, of course, has increased. Bioenergy is also increasing, and wind energy is also increasing. I see there is some chat, so please explain why China has less carbon released. So maybe I'll take up these questions a little later at the end of the talk.
Sure, ma'am.
Yeah. So now we look at the role of hydrogen. Of course, it's a very good, excellent energy carrier. And how do we produce hydrogen? There are various ways of producing hydrogen. And presently, a lot of research thrust is going into electrolyzing hydrogen from water. So if you have water and you use the solar energy, so we are talking about renewable and the greener ways of production of hydrogen. So if hydrogen is produced, you can take it to hydrogen storage and oxygen is released in air. This oxygen can also be used in hydrogen fuel cells as an input. So these hydrogen fuel cells, whatever energy is converted, can be stored into electric charge by batteries, and water, which is a byproduct, is released. So here we are talking about the green cycle of the hydrogen as an energy carrier. So slowly we are progressing towards the topic of today, which is battery versus fuel cell. So firstly, one has to understand what is the basic difference between battery and a fuel cell. So if you ask me, fuel cell is a energy conversion device, whereas a battery is a energy storage device. Of course, both these have very similar architecture. Yes.
No, ma'am, actually, accidentally, one mic was unmuted.
Okay, no problem.
You can carry on, please.
Yeah. So in both these devices, we are talking about the electrochemical nature of energy. So the energy production processes are taking place at the phase boundary of electrode and electrolyte in both the cases. Then we are talking about electron and ion transport in both of them, but both of them are happening in different um, along different paths. Okay, so when we read the word separated, what it means is that the ions flow in through a different path and electrons flow through a different path, and both of them have electrodes and an electrolyte solution, and electrical energy is generated by conversion of chemical energy via redox reactions at anode and cathode. So therefore, the connecting feature between them, between the battery and the fuel cell, is the electrochemical nature of energy. And anode reactions take place at lower potentials than the cathode. Then what is the power play? So first, let's look at this Ragon plot, which plots the energy density versus the power density. So capacitors, of course, are one another energy storage device, and here batteries, we have energy storage device. So if we look at these two entities, what is the difference? You can say that, capacitors, whenever you need a sudden burst of energy, their capacitors will be very helpful. And wherever you need a continuous flow of energy, in that case, batteries will be useful. So one example from real life which will help you in understanding the concept is, let's say that you have a dam, okay? So when the water is stored in a dam, the water, so the water is available, it has the energy. So whenever the doors or the gates of the dams are open, suddenly there will be a gush of water. In a similar way, in a capacitor or a supercapacitor, the charges can be stored on the electrodes, and on demand, there can be a sudden uh, release of energy through the capacitors. Now, in the same example, the dam example which I told you, let's now connect hypothetically certain pipes. Okay. So pipes are connected and they are of various diameters. So now when I need water, I need less water, I'll maybe use the pipe with a smaller diameter. When I need lot of water, I'll use a pipe with a larger diameter. So these batteries are functioning in that way that depending upon the demand of energy, they are controlling the flow or the rate at which the power will be delivered. So batteries are another feature which puts batteries and over here I have compared them with fuel cells because this is in connection with the previous slide, that batteries are actually closed systems, and whatever energy production is taking place is happening inside. Electrodes are the places where redox reactions are happening, and energy storage and conversion take place in the same system. Whereas if you look at the fuel cells, in fuel cells, you can have provision of providing the fuels, sorry, externally, and these are open systems. So whenever you turn on the supply of the fuel, the energy conversion will take place, and when you shut off the supply, you will not have any energy conversion taking place. Then again, the active masses are the ones which undergo the redox reactions. And as I've already mentioned, the fuels, the hydrogen and oxygen, if we talk about PMFCs, for them, the fuels are delivered from outside. Now we look at the difference between a battery and a cell. So if you have a cell, of course, each one of us have used the cells, a positive and a negative terminal is there. Now, this cell is capable of giving certain voltage only, okay? Now, if I connect multiple cells in series, that is what I get, a battery. So this is where the concept of cell and battery is arriving from. Now let's understand what is happening inside a lithium-ion battery. Why we are talking about lithium-ion battery? Let me just give you a quick overview over here. Sorry. When we talk about batteries, there are secondary batteries, and then we have primary batteries, and then we have secondary batteries. Primary batteries are those batteries which you can say are one-time use. Okay, we cannot recharge them. Secondary batteries are those generation of batteries which are rechargeable. So you would be seeing that you have, nickel metal hydride batteries which you can recharge. Then your laptop, your mobile batteries, these are all rechargeable. So now we come to why there's so much of hype around lithium-ion battery, and of course, its variants. So before we go into that, let's look into what is there inside a lithium-ion battery. This schematic is showing the processes of both charge and discharge. Okay, charging and discharging. So we'll follow one at a time. In a commercial lithium-ion battery, we have anode side, which is negative, sorry, and we have cathode, which is positive. Okay, usually the cathode is your lithium metal oxide, and anode is any graphite. So what happens when and you have a separator. Now the role of the separator is very, very, very critical. What it does is it first of all physically separates the cathode and anode. But beyond that, its very important feature is to allow the flow of only ions through it. So it acts as an insulator for electrons, and it passes the ions to flow through. So there is a whole field that talks about the chemistry of electrolytes or the separators. Okay, so that is not the subject of today. I'll be mostly looking at the electrode materials. But one thing we should not forget is, unless and until we create this separation of charges, that means ions are passing right to left and electrons are passing from the external circuit, we will not be able to extract any energy out of it. If electrons also flow through it, we are just creating a short between the two electrodes. So this is an important point, that the separator serves the function of passing the ions through it and not the electrons. Electrons flow through the external circuit, and whenever we connect a load out of it, we can extract work from this electrochemical energy, which is stored as a part of the in the anodes and in the anode and cathode. So just a quick recap of some fundamentals that you know, that the basic thermodynamics for any reversible reaction, in this case I've written electrochemical reaction, is given as delta G is delta H minus T delta S, where G is our Gibbs free energy, H is the enthalpy, T is the temperature, and S is the entropy. These G, H, and S are state functions. That means they only depend on the initial state of the function and the final state of the function. Now, when we talk about battery materials, of course, once we have constructed the once we have constructed the anode and cathode, we have used certain materials. So what type of materials they are, what are their chemical potentials, what all are their activities, all these get connected. And therefore, theoretically, you can predict that what is the Gibbs free energy for a given cell or a given battery. Okay. Then delta G, the Gibbs free energy, can also be represented as minus NFE, where N is the number of electrons transferred per mole of the reactants. F is a Coulomb constant, 96,400 Coulomb per mole, and E is the voltage of the cell with specific chemical reaction. So now so once I have created my electrodes, anode and cathode, I have made my choices of the materials. Delta G gets predefined over there. N depends upon the number of electrons. So if per mole only one electron is going to participate, or two electrons are going to participate, three electrons are going to participate. So that is how N is defined. F, of course, is constant. So you can predict the theoretical potential of the cell. Now, when we connect the cell or the battery, then the voltage drops at different points and due to various reasons. So let's understand what's happening. So if you look at the voltage, and this is the discharge current. Okay, so let's say you buy a battery, you buy a pencil cell, and you keep it in a cupboard, you don't use it. Maybe 4 to 5 years down the line, if you look at the if you use a multimeter to read the voltage of that cell, it would have dropped by itself. You have not connected it to any device. So these cells also have a shelf life, of course, because we're talking about all chemistry inside a small package. So here, if we see on the y-axis, the maximum voltage which a cell can deliver is called the open circuit voltage. That means the circuit is open, and if we just put the multimeter leads across its electrodes, it will read some potential, and that is known as the open circuit voltage. It is the maximum voltage which the cell can deliver. Now, when we talk about the lithium-ion battery, then what we see is as the cell is in use, sorry. So some discharge current flows. When this discharge current flows, it follows a certain profile. There are three regions defined in this profile. So if you look at the ohmic region, you'll see that it is linear, but beyond the regions, ohmic region, initially we have the activation region. I'll come to it in a while, maybe in 1 or 2 slides from now. And then we have the mass transport region. So this is how the voltage will drop across our um, battery. Now, if you remember, whenever if you talk to people who are working with batteries, they'll tell you that okay, whenever the battery is discharged, so 33%, please put it to charge, and whenever it is 100% charge or 90% charge, please remove it from the charger. The reason is that when you overshoot these limits, you are actually making the battery work in these regions. And of course, the reaction, the thermodynamics and the kinetics of the reaction tell us that these are reversible reactions. But if you operate them under the extreme regions of when the battery is giving out very low discharge current, you're actually forcing the battery to undergo what is known as the mass transport. That means the material will physically start leaving the electrode materials, and you're causing a physical damage to your battery. Of course, we can't see it from outside. Then again, whenever you are overcharging for a long duration of time, and if that is your habit, you're actually playing with the uh, life of your battery. So it's good if you operate it not at the extremes, but in this region. So here the changes are reversible, they are linear, and hence it will help in enhancing the battery life. I'm sorry, just a minute. So then over here you see the electrochemical series. This tells us, okay, so for different elements, you will see that certain reduction potentials have been written. So every cell that you talk about will have voltage with reference to certain potential given. And for us, it is the standard hydrogen electrode whose potential has been taken to be zero. It is something similar to what we do in physics whenever we solve for potential energy problems. You can treat the potential energy on the floor to be zero. You can take the reference of potential energy on any table to be equal to zero. Now, once you have chosen your reference, the potential energies will always be measured with respect to that reference. In a similar way, for quoting the cell voltages or the electrode potentials, we have certain standards. Over here, I'm showing you the standard hydrogen electrode. And so what it means actually is here the comparison is drawn that how easily or how difficult it will be for different elements to gain or lose electrons. So over here, if you see lithium, which is on the topmost side, it will readily take up an electron and combine to form lithium solid. On the other extreme, what you see is a silver ion will readily accept an electron and convert to a metal. So this is called the electrochemical series, and it tells us that how electrode potentials are defined. So going forward, we have two electrodes in the system. Cathode is where the reduction takes place. Reduction, as you know, is nothing but gain of electrons. Anode, on the other hand, oxidation reaction takes place, and anode is actually your uh, loss of electrons, which is happening. So in a conventional lithium-ion battery, In a conventional lithium-ion battery, the anode is made of carbon. Commercially, it is graphite. Cathode is some metal oxide of lithium. Different possibilities are there. It could be a lithium cobalt oxide, lithium iron phosphate, or lithium manganese oxide. An electrolyte is some lithium salt in an organic solvent. Then we talk about lithium metal as an anode. So if I use lithium metal as an anode, what are the challenges or one can face? So lithium metal anode, if you look at the electrochemical series, which I just showed you, it was highest over there. So what it means is it has two advantages. First of all, lithium is a light metal, okay? And other thing is that you can extract a lot of uh, potential from it, so energy from it can give. But theoretically speaking, things are different. Practically, things are different. So when one uses lithium metal as an anode, what happens is that in the charge and discharge cycles, there are some microstructural transformations which take place. These are spike needle-like spikes, which are called dendrites. I have a figure over here. I'll show you in a while. So what happens that the growth of these dendrites is inevitable. These are bound to happen. So what happens? This poses a threat to safety and stability of the battery. In one of my previous slides, I showed you the separator. Okay, so the job of the separator is that it has to keep physically the electrodes separate. Apart from that, the main function which it follows is that it should allow the flow of ions, but not that of electrons. Now, what happens is that these dendrites are very thin needle-like structures which keep growing. And when they grow, they are capable of piercing the separator. And once this piercing of separator happens, electrons find a channel to go to the other side, not via the external circuit, but through the internal circuit. And because a sudden rush of electrons is there, the device can get heated up. It can also create a short circuit. It can also catch fire. And in the commercial in the commercial cells or batteries, graphite is presently being used. So this is the structure of dendrites which are happening. You can see that these are very sharp needle-like structures which grow from anode towards the cathode. And once they pierce the separator, then we are actually talking about safety and stability issues of a battery. Now, what happens is when you are constructing a cell, then lithium metal, which is in contact with the electrolyte, it starts forming what is known as SEI, solid electrolyte interface. Sorry. What this solid electrolyte interface does is this part. What it does is that it forms a layer and it further stops the decomposition or deterioration of the electrolyte which is used. This SEI, it consumes some electrolyte, it consumes some lithium, and because of which the internal resistance of the battery rises. When different charge discharge cycles take place, large volumetric and morphological changes take place, and these are inevitable. Now, what happens? You can see that initially, let's say if this was lithium metal foil, then now it has protruded out. So volumetric changes have taken place, and these are unstoppable. These are unstoppable. And then the morphology has also changed now. So now these sharp ends or these sharp sides, these pockets will become regions where more reactions will take place. So therefore, these are unwanted, but we do not have a control over it. Just few years back, there was a paper in Science which talked about healing of lithium dendrites, where the authors have actually applied temperatures to heal these dendrites. So because we can't do away with these dendrites, by healing them, what you are actually doing is you are prolonging the life of your battery. But however, when you are healing it at higher temperatures, you are again consuming power from somewhere. So theoretically speaking or scientifically speaking, yes, it's doable, but practically perhaps it's not one of the best ways to get rid of the lithium dendrites. Then what are the other variants that are being researched upon these days? Sorry. So lithium metal battery I have talked about. What actually happens over here is whenever the cell is getting discharged, lithium ions move from the carbon composite, which is the anode, and they move towards the cathode. And while charging, lithium ions move from the cathode and back to the anode side. So when you are charging, let's say, a mobile battery or a laptop battery, what you're doing is you're removing the ions from the cathode side and making them move back to the cathode side. So the state of the battery is reset. Of course, it's not the same state. Some losses are always happening. Sorry. Then we talk about lithium sulfur battery. So here, sulfur also has a very high theoretical capacity. So that means it is capable of giving very, very high energy densities. But the problem with sulfur is that in between, when the cell is operating, there are certain uh, substances which are forming, and these are irreversible. Irreversible reaction takes place, and therefore you're slowly eating up the sulfur. And then they also start um, interfering with the um, functioning of the lithium sulfur battery. So theoretically, it is a good option. Then we have a lithium oxygen battery. So here, what is happening is that you are uh, from the air, the oxygen is helping in having the lithium metal oxygen rich environment, and the reactions are taking place by the oxygen in the air. So here, of course, we should have good amount of oxygen which reacts with the metal. So these are all the concepts where lithium-ion batteries are being used. Now I'll come to the last segment of my talk where I'll be talking about the anode variants. So as I told you that a graphite electrode is used usually, but with advancement, instead of graphite, we started moving towards other anode or other carbon-based anodes. Before I go to the other anode variants, let us quickly recapitulate what was the solid electrolyte interface. So as I told you that this is a layer which is formed whenever the electrodes are in direct contact with the electrolyte. So a passive layer forms, and in a way it helps because once uh, the exposed part to the electrolyte has this protective coating, you can say, it further does not allow the fresh electrolyte to come and meet this contaminated part. So you can say that it forms a part of passive layer, and therefore it also suppresses further deterioration or decomposition of the electrolyte, and therefore it plays a beneficial role in improving the safety and stability of lithium-ion batteries. So here you can see that this is a representative graph of voltage versus a specific capacity. The cell is being run at 100 milliampere per gram. When we say specific, we are actually dividing it by the active mass of the electrode. Why we do this? Because if I put more and more mass, of course, my ratings will improve, which is, you can say, is a kind of cheating. So we always talk about specific capacity, and hence divided by the mass of the active material. So here 100 milliampere per gram when the cell is operating, you can see that this is the first discharge cycle. So when you have just constructed the cell and use it in the first discharge cycle, it goes up to 1000 milliampere per gram capacity, specific capacity. And now these days, the companies are actually, whenever open a new mobile pack, they say that, okay, first charge will always going to take time. So this is the reason that, once the cell has first a discharge, it has reached over here, then the charging takes place. So again, you're going up the ramp from here, you're going up the ramp. This is the first charging cycle. And then as the cell is used, we have already talked about how the potential drops across the ohmic region, the activation region, and the mass transport region. So this initial drop which you are seeing over here is nothing but your formation of SEI phase. This passive layer is actually forming and eating up some of the voltage from your battery. So what are the different ways of minimizing it? You can make use of multi-volt carbon nanotubes. Now, so this graph is actually for multi-volt carbon nanotubes, and you can see that the SEI formation occurred in the voltage range from 1.5 to 0.5, where you can see that ohmic region, linear region is there. What are the other variants that we can have? Researchers have used graphene sheets. These graphene sheets are primarily produced from reduced graphene oxide and therefore have a lot of oxygen functional groups on their sheets. Because of these oxygen functional groups, the electronic conductivity of graphene is less. Just excuse me for a minute. Hello. Yeah. So we are dealing with low electronic conductivity of the synthesized graphene. Now, what these oxygen functional groups do, they also have an influence on the van der Waals forces on separate graphene sheets, and therefore they can um, favor agglomeration of the graphene sheets. Of course, we don't desire that. Why we don't desire that? Because if, let's say, hypothetically, if I have a graphene sheet isolated, then I will have its top surface and the bottom surface both available for uh, intercalation of lithium. And therefore, theoretically, what theory predicts is that you can form Li2,6. So for every lithium atom, you are having 3 carbon atoms on the graphene sheet. But in actuality, it doesn't happen because of all these reasons, the agglomeration takes place. So we don't get a perfect phase of Li2,6. If you talk about the multi-wall carbon nanotubes separately, which I just talked about, why multi-wall carbon nanotubes are used, first of all, they have a better conductivity, electronic conductivity as compared to the reduced graphene oxide. So therefore, they help us. Secondly, you can functionalize multi-wall carbon nanotubes by acid functionalization, and this can in turn help in keeping whatever you are going to make the composite for as separate. So here an example has been shown that if only graphene sheets are used and a composite of graphene and multi-wall carbon nanotubes are used, then when you construct the cell, you look at the first discharge curves on both the figures. For graphene, it is only reaching till a specific capacity of 600 milliampere hour per gram. Whereas when we talk about the graphene multi-wall carbon nanotube composite, it has gone almost up till 1350 milliampere per gram. And of course, when the cell operates, there is certain losses which are bound to happen. These are inevitable. So after 30th cycle, when only graphene is present, the specific capacity drops to about 250 milliampere hour per gram, whereas it stays beyond 750 milliampere hour per gram for the graphene multi-wall carbon nanotube composite. So we can see that this is faring better, far better than if we only have a graphene anode. So why the hybrid? The hybrid means the composite turned out to be a better anode material. There are several reasons to it. Few of them are listed over here. So first of all, whenever we have, we have used functionalized multi-wall carbon nanotubes. So these have a strong electrostatic interaction between the oxygen functional groups of graphene and multi-wall carbon nanotube. So what they do is they also help in creating or maintaining the space between graphene sheets. And once this is done, the agglomeration is automatically taken care of. So if a sheet, so for example, the schematic shows in between these sheets, if a CNT is found, then the CNT has a certain diameter and therefore these two sheets will not agglomerate. Dr. Pragya, how much time do I have?
Ma'am, you can take like 10 minutes time. Will it be sufficient for you, ma'am?
No, I'll finish it before that. I just wanted to
Ma'am,
know.
we want it to go on a completion. Whatever you have decided, please go with your flow. So if 5 to 10 minutes are required, ma'am, no, not an issue.
No, I think I'll be able to finish before that. So,
Sure, ma'am. Sure.
yeah, thank you. So, first of all, it helps in keeping the layers separate. It provides more surface area for the absorption of lithium, as you can see. So, intercalation is easier. Other benefit that comes in with using multi-wall carbon nanotubes as spacers is that not only the ions can pass inside the tube, as you can see. So this is also providing one more channel of hosting the lithium, and therefore it can host. So more charge means more capacity, specific capacity you will be able to get on the other side. And then it also improves the conductivity. It also helps in interconnecting these sheets. Okay. So many benefits are there for this hybrid that have been reported. People have also reported use of carbon dots or fullerenes C60 in graphene, and they have shown that the capacity increases if you have CNTs from 730 and to fullerene 784 milliampere hour per gram. Another aspect that is brought in because of these hybrid composites is graphene. First of all, is you can theoretically, if you look at it, it's a sheet, it's a planar surface. So if a lithium ion has to diffuse, it will diffuse faster through it. And these 3D interconnects, as I was talking about, so the lithium ions can also have a pathway in going from here to there. So it helps in better coordination between the different layers and the spacer layers by having a hybrid composite. And of course, it talks about better ion diffusion, wettability, and diffusion is better. Sorry. Next is some other metal oxides have also been used. I will skip this equation because these you can readily see in the literature that they're readily available. So why tin oxide? The tin oxide, if you look at the theoretical capacity, it has a very, very high theoretical capacity of 991 milliampere hour per gram. However, there are certain issues also with tin oxide. First of all, the agglomerations happen very fast because metal oxide nanoparticles agglomerate after a couple of cycles. Another is large volume expansion takes place. So there was a paper which talked about utilizing SNO2 in slightly different way, and this is the entire schematic. So what was done is that graphene sheets were taken, and these were functionalized with PSS. PSS stands for polystyrene sulfonate. So this polymer actually charges up or it creates, you can say, electrons on the graphene sheets. So this helps us in two ways. First of all, now since all the sheets carry, theoretically you can say the sheet is very beautifully uh, uh, negatively charged, but of course practically it will not be this perfect. So it serves two purposes. First of all, it will avoid any agglomeration of graphene sheets. Firstly, secondly, it gives us a tool to functionalize the sheets in a different way. So what is then done is that you once you have sulfonated these sheets, what you do is you add polypyrrole or do the polymerization with polypyrrole. So now polypyrrole also has, what it does is this has negative charge, this has positive charge. So it links perfectly well, because now you have now strengthened the electrostatic interaction between two polymers, the PSS and the PPY. And then what you do is you do the pyrolysis of this composite at 800 degrees centigrade in an inert environment. And what you're left with is the polymer goes away, it burns off. And what you have is the nitrogen from the polypyrrole is actually doped in your graphene sheets. So with this, what you do is you then decorate it with SNO2 nanoparticles. Now, this composite, that means SNO2 dispersed on nitrogen doped graphene, has shown excellent results. So here you can see that these are the TEM images and the SEM images of the composite. And if you look at the first discharge capacity, it has almost gone to 1750 milliampere hour per gram. And after 30th cycle, it is above 550 milliampere hour per gram. So the challenges which are faced in SNO2 were, as I told you, that two main issues are there: agglomeration of nanoparticles, and second is large volume expansion. So how these are taken care of due to these nitrogen doped graphene is as follows. Nitrogen doping, first of all, changes the electron charge distribution over the graphene sheet. This helps in better and uniform dispersion of SNO2 nanoparticles. And it has been reported that you get a very good size distribution when you have this kind of carbon support. The metal oxide nanoparticles also, which the particle size was about 2 to 3 nanometers. So you can see very, very fine metal oxide nanoparticles could be grown on to this. And therefore, because the size is so fine, the volume expansion, if it is happening, that is then you can say relieved by the graphene sheets. So if I have a bulky tin oxide particle sitting on a graphene sheet and a fine metal oxide nanoparticle sitting on the graphene sheet, the number of cycles which I will be able to run my battery with finer size particle will be much more whenever I have finer size particles. So this is what you can see in these two graphs. This is the stability of the cell created by SNO2 and SNO2 graphene support. So you can see that the discharge capacity decays. Okay, it's not flat. What we want is that it should give the same voltage, constant voltage for large number of cycles. So when you have this composite SNO2 nitrogen doped graphene, so you see almost that up till 100 cycles, the cell is able to maintain almost near about the same discharge capacity. So this composite has then helped in improving the performance of the cell as compared to if we only use the metal oxide particles or we only use metal oxide graphene support. Here, the nitrogen doping has also shown dramatic performance where the stability was quite a bit. Then before closing, I'll just touch upon lithium sulfur battery. I've talked about it in my previous lecture, the previous slide. But here, just 2 points of notice over here when you look at the sulfur. Okay, so we want to, of course, in a small battery, we need it to be a very, very powerful battery. So in the cathode materials, if the target is that if we have the lithium over here, then we should be able to get up to 4000 milliampere hour per gram. If we talk about what are the other variants that one can use, so lithium cobalt oxide I mentioned to you. Then lithium iron phosphate, F stands for ferrous, so lithium iron phosphate, and NMC stands for lithium nickel manganese cobalt. Okay, so these are the materials which are talked about. Why we start talking about lithium sulfur batteries is now wherever cobalt is coming into the picture, cobalt is slightly expensive as compared to sulfur. Sulfur is quite economical, and sulfur has high theoretical capacity also. So it will help in bringing down the cost drastically. Okay, So therefore, there is a lot of research thrust on lithium sulfur batteries. But problem is, as I told you, that there are certain products which form on the surface, and these are irreversible. So once these start forming and they coat the whole surface, the cell will quickly die down. So although theoretically it is possible to achieve higher uh, specific capacity from lithium sulfur batteries, but practically the challenging part of this shuttling effect is there, and therefore the cell cannot operate for long cycles. Also, other part is the large volumetric change. So the swelling also happens in the cell. Now you know that if anything which swells, first of all, will lose its mechanical strength also. So the integrity of the battery also is questionable in that case. So before I finalize, the thing roundup of our battery is that presently in the commercial rechargeable lithium-ion battery, the lithium cobalt oxide is used as the cathode and graphite is used as an anode. And it has a theoretical energy density of 387 watt hour per kg and measured energy density of 120 to 150 watt hour kg per kg. So presently, what are the options where research is going on? These are not yet commercialized. So these are that you can replace the cobalt with any other metal, and these metals could be iron, manganese, or nickel, or you can have layered structures. So if you read the literature, you will find many papers now coming up on lithium layered structures also. So with this, I would like to end my talk over here. These are a couple of references which were used. And thank you for your attention.
Thank you very much, ma'am, for your wonderful talk. Though it was sounding you are not so well today, but still, ma'am, you spared a lot of energy in explaining all the concepts. So thank you very much, ma'am. Now the session is open for the queries from the participant side. So if any participant is having any query, either they can raise hand or they can post their questions in this question answer box.
Hello.
Yes.
Pragya ma'am, I'm audible.
Yes, yes, yes.
Rupali ma'am, thanks a lot. It sounds that you are not well, but still your talk was so good, so informative. And being I am from a person who's working on rechargeable batteries, so I found it so interesting and so fundamental. My queries are like, as we all knew that lithium-ion batteries are exhausted. They are in both the ways. Lots of research has been going on. And the cost wise also lithium salts or lithium sources are being costly now. So people are working toward the sodium. So what is your view if we are moving towards the sodium ion batteries? And what are the limitations and what would be the advantage if we really go with sodium ion?
Well, see, research is going on. I completely agree with your point of view. But the kind of stability lithium has shown, it will take a couple of more years to reach to that stage. Yes, lithium is expensive. Lithium is not an environmentally friendly material. It has its own hazards. Purely sodium, if you ask me, it will be difficult. I mean, I have worked on lithium ion batteries, and another thing which I would like to showcase to you, you look at the history of lithium ion battery from its conceptualization to its commercialization. I think it's hardly 2 decades, and no other technology comes to my mind which has gone from conceptualization to its production in such, yeah. And it's still thriving. All the opponents are there, competition is there. It's still going to stay for some while. What I feel is it's going to be a tipping point where if you want to do away with lithium, perhaps in the longer run, what we could do is having the electricity grids where we have the renewable energy, and in terms of storage we have even the ultra capacitors or super capacitors coming in. So that's going to take a big load of lithium, of the lithium metal, and but it will stay. If you ask me today, it will stay.
Yeah. What is your
We
view
can't.
if we go? Yeah, if we go with the biodegradable polymer materials with lithium-ion battery, because so many people are working on this. But it is right.
Can
The
you repeat your
conceptualization
question?
too.
Can you repeat
My
your
query
question?
is my query is like from conceptualization to commercialization, people have started working on biopolymers also, biodegradable materials as well. But again, lithium ion is not so friendly with the bio materials, and I think this is the future which is required from the research side also. What is the possibility if we go with biopolymers for lithium ion?
See, again, the kind of, for example, if I have, let's say, hypothetically, I have this biopolymer which is giving me energy, right? Now I need, we are very impatient beings. Okay. I want my mobile. If my mobile battery is dying 50%, I need a quick charge. And I want maybe this charge to hold until 2 days. So that is why I said that I'm a little conservative person when it comes to lithium-ion battery. But there will be options, there will be alternatives. But to completely wash it away, presently, I don't see there is a possibility. We will have to go hand in hand with lithium for some time.
Right, right. Thank you very much. Thank you.
Dr. Pragya, there was a question on this.
Any other queries from the participant side? Yeah, ma'am.
In the chat box, there was a question, but if the participant can guide me to the slide, then that will be helpful.
I'm not able to see any question on my panels. So can you please help me?
What it says is that please explain why China has less carbon released. So if you can guide me to the slide, it will help.
Ma'am, I think it must be an older question, somehow prompting on today's chat box, I guess, because that question perhaps was asked in yesterday's webinar, I guess.
Okay.
So I'm not seeing any more queries right now, ma'am. And one more thing is that I'll share the email ID of yours with the participants so that if for some reason if they are not able to ask the question right now, they can have one-to-one discussion with you on your email contact.
Yes, that will be wonderful. Yeah.
And one more thing, ma'am. This basically this overall talk was about very basic concepts of the secondary batteries and the recent progress of the batteries. So I believe that it should be a treat for the people who are seeking for understanding the very basic concepts regarding this subject. And it would be a great favor to us if you could kindly share your presentation with us. If the data presented over here has already been presented and not, nothing to be kept. So if you could share, then maybe we can also share this with our participants as some of the participants had requested. And one more thing, ma'am, like the concepts you explained to us, if you can share some of the, so that the wealth of knowledge which you have transferred to the participants for their better understanding. With this,
sure, Dr. Pragya.
we are, yes, ma'am.
I'll share it with you. Just give me a couple of days. Let me just finalize. There are some unpublished results, so those can be just withhold, and other or maybe more information I can put in the slides before you share.
So not only a problem, ma'am, because we are having our FDP till 30th of September. So till that time, you can share these things with us. So I am really thankful to you, ma'am, for agreeing to deliver the talk, and out of your utmost busy schedule, you managed to give us this much time. So once again, thanking you so much.
Thank you.
And
Thank you very much. Yeah.
it was really wonderful to hear you and to, recall our earlier days.
Yes. It was wonderful, and thank you for this opportunity to connect. Yeah. Thank you,
Thank you so
everybody.
much,
Yeah.
ma'am.
Can I leave now? Yeah. Okay.
All of, yeah, sure, ma'am, sure.
Okay. Take care. Bye-bye.
All of us can leave now. Bye, ma'am.